Module 3, Lecture A, Lists, Tuples, Sets. By the end of this lecture, you will be able to use list, tuple, set, and frozen set to construct collections from various iterable sources, transform data between different collection types using built-ins while preserving or enforcing uniqueness and order as needed, and select appropriate collection constructors based on mutability, hashability, and typical access patterns. Building sequence collections, lists from iterables. Building a list from an iterable means turning a sequence of values, such as characters in a string or rows from a database, into a concrete collection stored in memory. As you traverse the iterable once, you gather each element into an ordered container that you can index and modify. This separates the original data source from how you work with the data, so you can revisit, analyze, and reuse the collected values multiple times without needing to access the original source again. Turning an iterable into a list lets you capture data that might otherwise be available only once, such as lines from a large file or rows from a database. By storing this data in a list, you create a stable snapshot in memory that you can revisit as often as needed. This makes it easier to sort, filter, and analyze the data repeatedly without going back to the original source. It is especially useful in data analysis, where you may need to compute statistics or look for anomalies multiple times on the same collection. Building lists from different kinds of iterables is important because it gives you a single, consistent structure for working with data that comes in many formats. Web frameworks may provide mappings, scientific tools may use generators, and user interface libraries may expose iterable objects. But turning them into lists lets you treat them all the same way. With lists, you can index, insert, and compare sequences reliably. This uniform approach makes it easier to manage and share data from diverse sources, such as configuration files or sensor arrays, throughout your program. Python code, lists from iterables. This section focuses on building lists from several iterable data sources and explains how these iterables are turned into concrete, indexable list collections. It shows that once data is collected into a list, you can access elements by position and work with the list as a stable structure. It also illustrates that after the original iterables are exhausted, the list still preserves their data, so it can be reused multiple times without needing to recreate the original sources. We begin with a text value that contains the characters N, Y, and C. We then use a function that converts this text into a list so that each character becomes its own separate element. This lets us work with each character individually. Finally, we display the list, which shows N, Y, and C as 3 separate items. We create a range of daily step counts, starting at 3,000, increasing by 2,000 each time, and stopping before 9,000. This range is then converted into a list so the values become concrete and can be accessed by position. Finally, we print the list to show the resulting step counts and demonstrate how the range has been turned into a sequence of numbers. This code defines a temperature generator function that loops through a list of Fahrenheit temperatures and uses the yield keyword to produce each value. Because it uses yield, the function becomes a generator, returning one temperature at a time instead of all at once. After yielding a value, it pauses until the next one is requested. This pattern is useful when working with large or continuous data streams, since it lets you process each item in sequence without storing the entire list in memory. We begin by using a temperature generator function that produces hourly temperature values, one by one. This generator is stored in a variable, so we can work with it. We then convert the generator's output into a list, which captures a fixed snapshot of all the temperatures it yields at that moment. This list is stored in another variable, and finally, we display its contents to show the collected temperatures from the generator. When we try to build a new list from the temperature generator, the result is an empty list because the generator has already been fully used once. Generators can only be iterated a single time, so any later attempt to read from them produces no values. Printing this second list confirms that the generator is exhausted. However, the original list we created earlier from the same generator is still intact and can be reused as needed. We reuse the list of temperatures that was created from a generator so we can process the data multiple times. With this list, we can apply a built-in function to find the maximum value, which gives us the highest recorded temperature. This shows that lists are useful for keeping data available for later analysis, even after the original source of the data cannot be used again. This script shows how to turn different kinds of iterables into lists, so they become concrete and indexable. It converts a string into a list of characters and a range into a list of step values. It also defines a generator that produces temperatures in Fahrenheit, then converts that generator into a list to capture a fixed set of temperature values. Once the generator has been used up, converting it again gives an empty list, but the list created earlier can still be reused. Finally, the script finds the maximum temperature in this list, illustrating that lists allow further analysis even after the original iterable is no longer available. Tuples as fixed records. Tuples are useful for storing fixed groups of related values that should not change, such as a geographic coordinate or a database record. Each position in the tuple has a defined meaning, like a name, a date, or a status flag. After a tuple is created from some source of data, both its structure and its contents are locked in. This immutability makes tuples a good choice when you want to represent a stable snapshot of data that must remain consistent over time. Tuples let you turn a simple sequence of values into a structured record. For example, when reading a log file, you can split each line into parts, such as timestamp, user ID, and action, then store them together in a tuple. Sensor readings like temperature and humidity at a given time can be grouped the same way. Because tuples are ordered and cannot be changed, they keep the relationship between fields clear and help ensure that important data stays consistent. Tuples are useful as fixed records because they help structure data and improve safety, especially when combined with other collections. For example, a list of tuples can store a class roster, and a set of tuples can represent connections between cities. In these cases, each tuple is a meaningful record, while the surrounding collection organizes many such records. Since tuples are immutable, they can be used in sets or as dictionary keys providing stable, hashable values. This turns raw sequences into structured representations of real-world entities and events. Python code. Tuples as fixed records. Tuples can be used as fixed records to represent simple delivery stops, such as a specific location and time. You can build these tuples from other iterables and then store them inside larger collections like lists or dictionaries. Because tuples are immutable, their contents cannot be changed after creation, which makes them safe and reliable to use as dictionary keys when you need stable records. We create a list called stops data that holds information about delivery stops. This list contains 3 smaller lists, and each smaller list represents one stop. Each stop includes the stop name, the scheduled arrival time, and the distance to that stop in miles. Using this consistent structure makes it easy to manage and access the details for each delivery stop. We take the existing list of delivery stops, where each stop is stored as a list of details like name, time, and distance, and convert each inner list into a tuple using a list comprehension. This creates a new list called stops records, where every element is now a tuple. Tuples are immutable, meaning their contents cannot be changed after they are created. This immutability makes them well-suited for representing fixed delivery records and helps keep the data stable and consistent throughout the program. We begin by printing a short message to let the user know that delivery stops will be shown as fixed tuple records. Then, we loop through the list of stop records, and for each one, we print the entire tuple. This simple process displays each delivery stop's details in turn and illustrates how tuples can be used to represent fixed, structured records in a clear and consistent way. We create a dictionary called travel times that uses tuples as keys, where each tuple represents a pair of delivery stops. For instance, a tuple containing stop A and stop B serves as one key. The value stored for each key is the travel time in minutes between those 2 stops. This works well because tuples are immutable, meaning they cannot be changed, which makes them reliable and stable as dictionary keys. We begin by printing a short message to introduce the travel times between delivery stops, so the listener knows what the data represents. Then we loop through each entry in the travel times dictionary, where each key is a pair of stops and each value is the travel time in minutes. For every pair, we print the 2 stops, followed by the word takes and the number of minutes. This produces a clear, readable list of how long it takes to travel between each pair of stops. We begin by taking the first element from the list of tuples that represent our delivery stops, using its position in the list. This first stop record is then stored in a variable for later use. We also print a message explaining that this first stop is an unchanged tuple. This emphasizes that tuples are immutable, meaning their contents cannot be modified after they are created, which helps protect the integrity of the stored data. This script shows how tuples can be used as fixed records for delivery stops. It converts a list of lists into a list of tuples, so each stop is stored as an immutable record with a name, time, and distance. These tuples are then used as keys in a dictionary to map travel times between stops, demonstrating that their immutability makes them suitable for this purpose. The script also confirms that the first stop tuple does not change, emphasizing that tuples help maintain stable, consistent records. Copying versus referencing. When you build new lists or tuples from existing data, it is important to know whether you are creating a true copy or just another name for the same object. Simply assigning one list to a new variable does not make a new list. Both names refer to the same data in memory, so any change through one name appears in the other. In contrast, using a constructor that builds a list or tuple from an existing iterable creates a new collection with its own identity. As a result, changes to the original will not affect this new collection, even if they started with the same elements. When recording collections as daily snapshots, such as investment portfolios, you should create independent copies instead of reusing the same list. Using a list or tuple constructor makes a separate copy of the data for each day. Tuples are especially useful because they are immutable, so the structure of each record cannot be changed by mistake. The individual objects inside the tuple can still be reused, but the overall snapshot remains fixed. When you build a new list, tuple, set, or Fosen set from an existing iterable, you create a shallow copy, meaning the outer container is new, but it still refers to the same elements inside. This is usually fine when the elements are immutable values, like numbers or strings, because they cannot be changed in place. However, if the elements are mutable objects, such as inner lists, then modifying one of those inner objects will be visible in every container that refers to it. Understanding this behavior helps you decide whether a simple constructor is enough, or if you need a more advanced copying approach that also separates the inner elements. Python code, copying versus referencing. This lesson uses simple shopping cart items to show the difference between referencing and copying lists. When two names both reference the same list, changing the list through one name automatically changes what you see through the other. In contrast, when you make a true copy of a list, each list can then be modified independently without affecting the other. The same idea applies to tuples, which also remain independent when copied, even after structural changes are made elsewhere. Imagine a shopping cart list with items like apples, bread, and milk. An alias of this cart is not a new list, but another name pointing to the same data. So any change through the alias also changes the original. A copy of the cart, created as a shallow copy, is a new list with the same items that will not be affected if the original list changes. Finally, a snapshot stored as a tuple is an immutable version of the cart that preserves the items as they were at the moment it was created, even if the original list is later modified. We use the identity function to show how different references relate to the same or different objects in memory. The original shopping cart list has one memory address, and its alias points to that exact same address, proving they are the same underlying list. The copied cart, however, has a different memory address, so it is a separate list, even though it starts with the same items. The snapshot tuple also has its own distinct address and represents an immutable version of the original list. When we add an item like eggs to the shopping cart using an alias, we are actually changing the original list because the alias points to the same underlying object. Printing the original cart then shows that eggs has been added. In contrast, when we print the copied list, it does not include eggs, which shows that the copy is separate from the original and does not reflect later changes. Finally, printing the snapshot stored as a tuple also shows no change, highlighting that it is both independent of the original list and immutable. We create a nested list made of two inner lists, then make a shallow copy of the outer list. In a shallow copy, only the outer list is duplicated, while the inner lists are still shared between the original and the copy. When we modify the first inner list in the original by adding a new item, that change also appears in the copied list because they point to the same inner lists. Printing both lists shows that the inner modification is visible in both, illustrating how shallow copying affects nested structures. This explanation shows how referencing and copying lists work in Python. When you create an alias of a list, both names point to the same underlying list. So changing one, such as by adding an item, also changes the other. A shallow copy, however, creates a new outer list, so changes to the alias do not affect that copied list, and a tuple snapshot is completely immutable and stays the same even if the original list changes. In a nested list, a shallow copy only duplicates the outer structure, so the inner lists are still shared, and modifying those inner lists is reflected in both the original and the copy. Building sets from collections. Sets for uniqueness. When working with data collections, sets are useful because they automatically keep only unique values. Converting a list or other collection into a set removes duplicates for you, so you do not have to check for repeats manually. This is especially helpful with things like email lists, survey responses, or product IDs, where you care about which items appeared, not how many times each one was repeated. When converting data between different collection types, sets are useful for cleaning and normalizing by enforcing uniqueness. For example, if you have a list of user actions and only care about which actions occurred, turning the list into a set will keep just the distinct actions and ignore order. After removing duplicates, you can convert the set back into an ordered collection, such as a list or tuple. In this way, sets act as a uniqueness filter before you move the data into whatever format you need next. When you use sets to ensure uniqueness, you give up any guarantee about the order of elements, unlike lists. Even if a set seems to keep a stable order, you should not rely on it. Sets are ideal when you only care about which unique values exist, such as the different cities your customers come from. If you also need a specific order, first use a set to remove duplicates, then convert the result back into an ordered collection by sorting or applying your own ordering. In short, sets provide a clean, duplicate-free group of values that you can later reshape into whatever order your program needs. Python code. Sets for uniqueness. Sets automatically remove duplicate values, so they are useful when you need uniqueness. You can start with a list that contains repeated values and convert it to a set to keep only one copy of each value. By comparing the original list with the resulting set, you can clearly see which duplicates were removed. If you then need the unique values in a specific order, you can convert the set back into a list and sort it to get an ordered collection of unique elements. We begin with a list of city names that includes repeated entries for places such as Boston and Dallas. These repetitions represent multiple orders coming from the same city. The main goal of using this list is to show how duplicate locations can be identified and removed in later steps. We begin by showing the original list of city names, which still contains duplicates. This list comes from several orders and includes every city exactly as it was first recorded, even when the same city appears multiple times. By printing this full list, we can clearly see which city names are repeated. This prepares us to demonstrate how to remove duplicates and create a list of unique city names in the following steps. We start with a list of city names that may include duplicates and convert it into a set to keep only unique names. This conversion automatically removes any repeated entries. However, sets are unordered collections, so while we gain uniqueness, we lose the original order of the cities in the list. This line prints the set of unique cities, which filters out any duplicate city names from the original list. A set automatically keeps only one copy of each city, so every name appears at most once. However, it does not preserve the original order of the cities. This is useful when you only care about which distinct city names are present, not the sequence they were listed in. We take the set of unique city names and turn it into a sorted list. This means each city appears only once, and the cities are arranged in a defined order. Having them sorted makes it easier to use these names in reports or any later steps where the order of cities is important. We finish by printing an ordered list of unique city names. To create this list, we first convert the original list of cities into a set to remove any duplicates. We then sort the set so the city names appear in alphabetical order. This produces a clean, readable list that is easier to use for reporting or displaying the data. This example shows how Python sets can be used to keep only unique values by removing duplicates. It starts with a list of city names that includes repeated entries, then converts that list into a set so that each city appears only once. When the set is printed, you can see that duplicates are gone and the original order is not preserved. Finally, the set is turned back into a sorted list, producing an ordered list of unique city names. This demonstrates how sets help manage and report unique data efficiently. Immutable sets as keys. When you need unique items in a collection, it helps to know the difference between regular sets and frozen sets. Regular sets can change, so you can add or remove elements, which means they cannot be used where a stable, hashable object is required, such as dictionary keys. Frozen sets are fixed after creation, so they are hashable and can safely be used as keys or as members of other sets. This immutability makes frozen sets useful for representing complex categories while still allowing fast lookups. You can think of a frozen set as a stable snapshot of unique items that acts as a reliable identifier in your data structures. Immutable sets are useful as dictionary keys when you need to map combinations of items to values, such as recommending products based on what a customer bought. While the customer is still shopping, their basket can be a regular, changeable set. Once the basket is final, you convert it to an immutable set so it becomes hashable and safe to use as a key for storing and retrieving recommendations consistently. This same idea applies in other areas, like grouping students by the courses they take or categorizing articles by their keywords. Switching between mutable and immutable sets lets you stay flexible while preparing data and still be safe and efficient when doing lookups. You can start with a list or other iterable, turn it into a regular set to remove duplicates and combine sets, then convert it to an immutable set once the contents are final. This immutable version is hashable, so it can be used as a reliable key when storing or indexing data. For example, you can build dictionaries where immutable sets represent tags or attributes, and the values store counts or configurations. By choosing when to freeze a set, you control exactly when a collection stops changing and becomes a stable identifier in your program. Python code: immutable sets as keys. This lesson shows how to safely use immutable sets as keys in a dictionary. It explains that you should convert any mutable set into an immutable frozen set before using it as a key. By doing this, you can reliably map different combinations of items to simple recommendation messages. The focus is on using frozen sets to keep dictionary keys stable while still representing flexible item combinations. We define two shopping baskets for Alice and Bob, each represented as a mutable set that stores the unique items they choose. Alice's basket contains milk, bread, and eggs, while Bob's basket contains bread and butter. Using sets is helpful here because they automatically remove duplicate items and make it efficient to check whether a particular product is in a customer's basket. This makes them a practical choice for managing shopping items. We convert each mutable set that represents a customer's shopping basket into an immutable frozen set so it can be used as a dictionary key. This step is important because regular sets can change and therefore cannot serve as reliable keys. By using frozen sets, we ensure the keys stay fixed and unchangeable. This allows us to consistently map each specific combination of items to its corresponding recommendation in the dictionary. We create a dictionary whose keys are frozen sets, which are immutable sets, so the keys stay fixed and valid for dictionary operations. Each frozen set represents the exact combination of items in a shopper's basket. For example, Alice's basket as a frozen set maps to a recommendation for cereal with a milk discount, and Bob's basket maps to a recommendation for jam to go with butter. Using frozen sets in this way lets us reliably look up recommendations based on specific item combinations while keeping the dictionary keys stable. We first print Alice's basket key, which is the immutable version of her shopping basket, to see how it appears inside the dictionary. Then, we look up her recommendation using a newly created immutable set built from the same basket items. This shows that even when we recreate the key from scratch, the dictionary still finds and returns the correct recommendation. In other words, using an immutable representation of the basket ensures consistent and reliable access to the stored values. Alice's shopping basket is a mutable set, so when we add cookies to it, the set itself is changed to include the new item. We then print the basket to show its updated contents. This example illustrates that even though the original set changes, the frozen set that was created from it and used as a dictionary key does not change. As a result, the dictionary key remains stable and reliable despite later modifications to the original mutable set. We first print the original immutable key, which is the frozen set created from Alice's shopping basket. to show exactly what is stored in the dictionary. Then, we look up the recommendation linked to this key. This illustrates that even if Alice's original mutable set of items changes later, the frozen set used as the key does not change, so we can always retrieve the same stored recommendation reliably. This example shows how immutable sets, called frozen sets, can be used as stable keys in a dictionary. It begins with 2 shopping baskets for Alice and Bob as regular changeable sets, then converts them into frozen sets to use as keys that map to recommendation messages. Looking up Alice's basket returns a cereal discount recommendation. Even after adding a new item to Alice's original set, the frozen set key does not change and the same recommendation is still returned. This demonstrates that frozen set keys remain fixed and reliable for dictionary lookups, regardless of later changes to the original mutable sets. Converting lists to sets. Changing a list to a set changes both how the data is stored and what it means. A list keeps the order of items and allows duplicates, which is useful when the sequence or repetition matters, such as tracking button clicks. A set is unordered and automatically removes duplicates, keeping only unique elements. So when you convert a list to a set, you are choosing to ignore order and frequency in exchange for a simpler collection of distinct values, like turning a list of scanned product IDs into just the unique products that were scanned. Converting a list to a set is useful when you need each item to be unique and want quick checks for whether something is included. For instance, turning a list of email addresses from sign-up forms into a set automatically removes duplicates. This makes it easier to see if a particular address is present. However, you lose the original order and any information about how many times each address appeared. Therefore, this approach is best when uniqueness matters more than order or frequency. Converting a list to a set is a quick way to remove duplicate values, because a set automatically discards repetition and does not keep order. For example, if you have a list of city names from user profiles or tags, course codes, or ingredients, turning it into a set gives you only the unique items. If you still care about order, you can then convert the set back into a list and sort it. The important idea is to switch between lists and sets intentionally, so you keep order when needed, while using sets to simplify repeated values. Python code, converting lists to sets. You can use sets to quickly remove duplicates from a list and to check whether a value is present. When you convert a list to a set, any repeated elements automatically disappear, leaving only unique items. This makes membership checks efficient and ensures you are working with distinct values. If you need the unique elements in a specific order, you can then convert the set back into a list and sort it for a clean, ordered presentation. We begin with a shopping list made up of strings that represent product identifiers. Some items, such as milk and eggs, appear more than once to mimic products being scanned multiple times. This setup prepares us to show that when we convert the list into a set, all duplicate entries are removed. In this way, the example highlights that a set keeps only unique elements from the original list. We begin by displaying the original shopping list, which is a sequence of product identifiers. It is important to show this list exactly as it was created, because it may contain duplicates and preserves the order in which items were added. Seeing the unmodified list first makes it clear where repeated items occur. This provides a clear baseline before we apply any method to remove duplicates or change the list. We convert the shopping list into a set to automatically remove any duplicate items. A set keeps only unique product identifiers, so any repeated entries are discarded. This makes the set data structure ideal when we need to enforce uniqueness in the list of products. We print the set of unique products to show that any duplicate values have been removed and that the original order is not kept. This demonstrates that a set stores only one copy of each element. It also helps clarify how sets differ from lists in both how they store data and how we retrieve it. We take the set of unique products and turn it back into a list so we can sort the items alphabetically. Sorting gives us a clean, ordered view of the unique products. This makes the list more consistent, easier to read, and more useful for things like reports or user interfaces. This code takes a list of products, removes any duplicates by converting it to a set, then sorts the remaining items alphabetically. The result is a clean, ordered list where each product appears only once. This makes the output easier to read and understand since it clearly shows all the unique products from the original list in a consistent order. We set a variable to the value milk to represent the product we want to check in our collection of unique items. We then use a set to test whether this product is present. Using a set makes this membership check more efficient because set lookups are generally faster than checking through a list. This allows us to quickly determine if milk is one of our unique product identifiers. We check whether the item milk is contained in the set of unique products using a membership test. Sets are designed to make this kind of check very efficient. The program then prints the result, indicating if milk is present in the unique product set or not. This script shows how to remove duplicates from a list by converting it into a set, which automatically keeps only unique items. A shopping list with repeated entries like milk and eggs becomes a set where each item appears once, though the original order is lost. The set is then turned back into a list and sorted alphabetically to produce an organized list of unique items. Finally, the script checks whether milk is in the set, demonstrating how sets support fast membership tests and are useful for ensuring uniqueness before creating a sorted list. Choosing Python collections. Mutability in collections. When choosing Python collections, focus on whether they are mutable or immutable, because this affects how their contents can change and how safely they can be shared. Mutable collections, such as lists and sets, let you update elements and work well for data that needs to evolve. Immutable collections, like tuples and frozen sets, cannot be changed after creation and are better for stable data. Matching the mutability of a collection to how stable your data should be helps prevent bugs and makes your program easier to reason about. Mutability determines how collections behave when shared between parts of a program. If you pass a mutable collection to a function, that function can change the original data, which is useful for updating shared state, such as logs or task lists. However, this can also introduce unintended side effects if the caller assumes the data will stay the same. Immutable collections, such as tuples, avoid this problem by preventing changes to their contents which is especially helpful in concurrent programs where it reduces the risk of race conditions. Mutability influences how collections behave and perform. Mutable collections, such as lists and sets, are useful when data needs to change frequently. Immutable collections, such as tuples, are better when you need stable identifiers, for example, as dictionary keys, because they cannot be altered. Even when not used as keys, immutable collections clearly signal that their contents are fixed. Choosing between mutable and immutable collections is an important design decision that affects how data is used and how reliable a system is. Python code, mutability in collections. Use a simple shopping cart example to show the difference between mutable and immutable collections. A list-based cart can change after it is created, so you can add or remove items, while a tuple-based cart stays fixed and cannot be altered. Explain that when functions receive these collections, they can safely read or modify them depending on whether they are mutable or immutable. Emphasize that mutable collections can be changed in place, which can lead to unsafe side effects when shared, while immutable collections prevent such unintended modifications. We begin by creating a shopping cart as a list, which is a type of collection in Python that can be changed after it is created. The list is initialized with 3 items: apples, bread, and milk. Because this collection is mutable, we can later add, remove, or modify items in it. This simple setup is used to demonstrate how mutable collections work when programming with lists in Python. In this example, we use a tuple to represent a shopping cart that holds the items apples, bread, and milk. A tuple is immutable, which means that once it is created, its contents cannot be changed. This is different from a list, which can be modified after creation. Using an immutable structure like a tuple is helpful when you want to guarantee that the data in your program stays fixed and cannot be altered by mistake. We begin by showing the original contents of both the mutable list and the immutable tuple to create a clear starting point for comparison. The first print statement displays the initial items in the shopping cart stored in the list, and the second shows the original state of the tuple. By establishing this baseline, we can later see how changes affect the list while the tuple remains unchanged, highlighting the difference between mutable and immutable collections. Inside the function, we try to change both mutable and immutable collections passed as arguments, starting with the mutable list. When we append the string eggs to this list, we directly change its contents. Because lists are mutable, this modification inside the function also changes the original list outside the function. This behavior illustrates how mutable collections can be altered in place when passed to a function. When the code tries to change an immutable tuple by adding the item eggs, it actually creates a new tuple that combines the original items with the new one. The original tuple stays exactly the same and is not altered. This behavior shows that tuples cannot be modified after they are created. Any apparent change to a tuple is really the creation of a new tuple with the desired contents. Inside the function, we first show that the mutable list has changed by printing it after adding the new item, eggs. This confirms that the original list was directly modified. We then print the new tuple created by joining the original immutable tuple with an extra element. This shows that the original tuple stays the same, and instead, a separate updated tuple is produced. we call a function named updateCarts with two arguments: a list version of the cart that is mutable and a tuple version that is immutable. This function is used to show how these two collection types behave differently when we try to change them. Inside the function, the list can be directly modified, and those changes are visible outside the function. In contrast, the tuple does not change outside the function, which illustrates the idea of mutability and immutability in Python collections. When we print the shopping cart list after calling the function, we see that the new item has been added because lists are mutable and can be changed in place. In contrast, when we print the shopping cart tuple, it is exactly the same as before the function call. Even though a new tuple with an extra item was created inside the function, that change does not affect the original tuple outside the function. This illustrates how mutable collections, like lists, can be modified by a function, while immutable collections, like tuples, remain unchanged. This example uses a shopping cart to show the difference between mutable and immutable collections. A list and a tuple both start with the same items, but the list can be changed while the tuple cannot. When a function adds eggs, it directly updates the list, but it must create a new tuple instead of changing the original one. After the function runs, the list now includes eggs, while the original tuple outside the function stays the same. This illustrates that mutable collections can be modified in place, whereas immutable ones require creating new versions to reflect any changes. Hashable collection choices. When choosing a collection type in Python, think about whether the collection or its elements need to be hashable so they can be used as dictionary keys or set elements. Hashable objects have a stable identity and a consistent hash value. Immutable types, like tuples, are hashable as long as all their elements are hashable, while mutable types, like lists and sets, are not. For composite keys, such as combining a country code and a year, tuples work well because they bundle multiple values into a single immutable unit, suitable for dictionary lookups or set membership checks. In Python, the key difference between a set and a frozen set is that a set is mutable, so you can add or remove elements, while a frozen set is immutable. Because sets can change, they cannot be used as dictionary keys, but frozen sets can, since they are fixed and hashable. This makes frozen sets useful when you need to treat a group of unique items as one stable value. For example, in a recipe recommendation system, you can represent a combination of ingredients as a frozen set, so you can cache results efficiently without worrying about the order of the ingredients. When choosing a hashable collection in Python, think about how you will use it in your data structures and algorithms. If you need to keep a specific order and position and also use the collection as a key or set element, a tuple is usually best, as long as all its elements are hashable. If order does not matter and you just need a unique set of items as one hashable value, a frozen set is more appropriate. By preferring tuples or frozen sets instead of mutable types, you help keep your data structures consistent and efficient for fast lookups and caching. Python code hashable collection choices. This section shows how to choose hashable collections such as tuples and frozen sets, when you need to use them as dictionary keys. It explains which types of collections are safe for this purpose and which are not. You will compare how mutable collections behave differently from immutable ones during simple dictionary lookups. The goal is to understand why immutability is important for reliable key behavior in dictionaries. We create a tuple to use as a key in a dictionary, representing a travel route between New York and Chicago by train. A tuple works well here because it is immutable, meaning its contents cannot be changed after it is created. This immutability makes the key stable and dependable, so dictionary lookups using that route remain consistent and accurate. We define a dictionary entry where the key is a tuple that represents a route between two cities, and the value is the travel time, set to 18 hours. This tuple acts as a composite key because it combines both cities into a single key. Using a tuple in this way works because tuples are immutable and hashable, which makes them valid and reliable keys in a dictionary. We look up the travel time in the dictionary by using the same tuple key that was used when storing it. This shows that tuples as immutable collections can be used reliably as dictionary keys. Because they do not change, they consistently point to the correct value. In this example, that value is the number of travel hours for a specific route. A frozen set is an unchangeable version of a set, so once you create it, its contents cannot be modified. Because it is immutable, it is hashable and can be safely used as a key in a dictionary. In this example, the frozen set holds the ingredients flour, eggs, and milk. Using a frozen set for this group of ingredients lets us reliably use that collection as a dictionary key, which is important for tasks like caching results or performing quick lookups. We use a frozen set as the key in a recipe cache dictionary that maps a set of ingredients to a specific recipe suggestion, such as a pancake recipe. The key idea is that a frozen set is immutable, meaning it cannot be changed after it is created. This immutability makes it safe and reliable to use as a dictionary key. In contrast, a regular set is mutable and therefore cannot be used as a dictionary key. We create a new frozen set containing the ingredients milk, flour, and eggs, and use it as a key to look up a value in the recipe cache dictionary. Because frozen sets are immutable and hashable, they can serve as dictionary keys, and their element order does not matter. This means our new frozen set matches the existing key in the cache, even if the ingredients are listed in a different order. Using this key, we retrieve and print the stored pancake recipe suggestion from the dictionary. In this example, we try to create a set with the elements flour, eggs, and milk, and then use that set as a key in a dictionary with some string value. When we do this, Python raises a type error because regular sets are mutable and therefore not hashable. Dictionary keys must be hashable so they can be looked up reliably. By catching the error and printing its type, we confirm that the problem comes from using a mutable set as a dictionary key. This script shows how immutable or hashable collections can be used as dictionary keys in Python. It first uses a tuple to represent a travel route and stores a travel time under that key, then successfully retrieves the value using the same tuple. It then uses a frozen set of ingredients as a key to cache a recipe suggestion and demonstrates that recreating the same frozen set allows reliable access to the stored recipe. Finally, it attempts to use a regular set as a dictionary key, which fails with a type error, emphasizing that mutable collections, like sets, are not hashable and cannot be used as dictionary keys. Overall, the example highlights that only immutable collections are suitable for use as keys in dictionaries. Membership and lookup costs. When choosing between lists, tuples, and sets, think about how often you need to check whether a value is present or access an element by its position. Lists and tuples test membership by scanning elements one by one, which is simple but becomes slower as the collection grows. This is usually acceptable for small collections or rare checks, but for large data or frequent lookups, such as in web services or data analysis, the type of collection you choose can have a significant impact on performance. Sets and frozen sets are designed for very fast checks of whether an element is present, using a hash-based structure that stays efficient even as the collection grows. This makes them well-suited for tasks like managing blocked IP addresses or checking if a word is in a dictionary, where you mainly need quick yes or no answers. However, they do not support accessing elements by position and treat their contents as unordered, so they are not appropriate when you need to keep or rely on a specific processing order. When choosing a collection type, think about how you will access its elements. Lists and tuples are best when you need fast, predictable access by position, such as getting the fifth item. Sets and frozen sets are designed for quick membership checks and operations like union or intersection, but they do not let you access elements by index. If you often find yourself converting a set to a list just to use positions, you probably should use a sequence type instead. A common pattern is to use a set for fast membership testing, then move the results into a list when you need an ordered collection for further processing. Python code, membership and lookup costs. This section focuses on checking whether values are members of lists and sets, and on comparing how long these lookups take. You will see how the cost of membership tests changes as the size of each collection grows. By comparing timing results, you can understand the performance differences between lists and sets. This helps you choose the most appropriate collection type when your program needs to perform frequent membership checks. The script starts by importing the timeit module from Python's standard library, which is used to measure how long small pieces of code take to run. This tool is helpful for performance testing and optimization because it lets us compare the speed of different operations. In this case, it is used to time how quickly membership checks are performed in two data structures, lists and sets, so we can evaluate which one is more efficient. We create a large collection of user identifiers by first generating a list of sequential numbers from 0 up to 500,000. This list holds all the user identifiers in order. We then convert this list into a set that contains the same identifiers. This conversion is important because sets use a hash-based structure, which makes checking whether a user identifier is present much faster than checking in a list. We choose a value that is definitely not in either the list or the set by taking the size of the collection and adding 1. This guarantees the element is absent, so when we check for membership, we are always measuring the case where the search fails. Using this setup, lets us fairly compare how long membership checks take in large lists versus large sets under worst-case conditions. We use a helper function that checks whether a given user identifier appears in a list and returns a true or false result. The identifier is intentionally chosen so that it is not in the list. This setup lets us measure how long it takes to perform a membership check in a list. By timing this operation, we can compare the performance of lists with other collection types, such as sets. A check-in-set function is used to see whether a particular user identifier, which is known to be missing, is present in a collection of user identifiers. It returns true if the identifier is found and false if it is not. This works efficiently because the collection is implemented as a set, which in Python uses a hash table. As a result, checking membership typically takes constant time on average, making this approach well-suited for frequent membership tests. We use the TimeIt module to measure how long it takes to check whether a user who is not present appears in a list, repeating the check several times to get a stable average. We then do the same measurement for a set. Comparing these two timings shows the performance difference between membership checks in lists and sets. This code measures and prints how long it takes to check whether a non-existent element is in a list and then in a set. For each structure, it reports the time taken, rounded to 4 decimal places. By comparing these two times, you can see the performance difference between list and set membership checks. This helps illustrate why the choice of data structure matters for efficiency in Python. The code compares how long membership tests take in a list versus a set. If the list is slower, it recommends using sets for frequent membership checks in large collections. If the list is similar in speed or faster, it notes that the collection size or the specific environment may have affected the results. Overall, the output guides you on whether a set or a list is more efficient for your situation. This script measures how fast Python can check whether a value is present in a list compared with a set. It builds a large list and an equivalent set of user identifiers, then repeatedly tests for an identifier that is not in either collection to simulate the worst case. Using the time measurement tool, it records how long these membership checks take for each type of collection. The results show that sets are generally faster than lists for membership tests in large collections because sets use a hash table that gives, on average, constant time lookups. Based on this, the script recommends using sets when you need to perform frequent membership checks on large amounts of data. In this lecture, you learned to use list, tuple, set, and frozen set to construct collections from various iterable sources. Transform data between different collection types using built-ins while preserving or enforcing uniqueness and order as needed. And select appropriate collection constructors based on mutability, hashability, and typical access patterns. In the next lecture, Lecture B, we will go over dicts and views. Thank you for your attention. See you all in the next lecture.